So hi everyone, thanks for letting me come out here over video to talk about the Solar System Working Group contribution to the CASTOR science mission. There's a fair list of names here of people who've been contributing to this project's development over time. And I'm just going to walk you quickly through our major kind of points. So I just want to remind you, here's a beautiful image from James Webb of the Fomalhaut disk. And you can see there's a little knot of dust here, which seems to be related perhaps to some kind of star forming process that might be going on. There are gaps, there's rings, there's all kinds of things going on that relate to the process of planet formation, within this system. This was taken with James Webb using MIRI. So what we think happened in the solar system early on was there was a disk of material that was down here, somewhere between, say, 10 and 20 astronomical units. Then the giant planets started to migrate outward, and as they migrated outward, they interacted with that disk of material and scattered it all up into this zone of the solar system. That created one component of the population of the outer solar system, but it left, there was probably initially much sort of way down here, a low inclination component that formed in situ and still there, but isn't part of this model. So we think basically we can probe where these different parts of the solar system formed if we can look at the surfaces of the objects and understand their cometary activity of material that came from these source regions and see what drives that cometary activity. We can look at the size distributions of the objects. We can look at their surface properties. It's going to tell us all about this process of planetesimal formation. Another piece that we seem to be getting our hands on now is this idea of how planetesimals form. So in this little model here, what you can see is there's, it starts off with a big cloud of dust, and as that dust cloud evolves, it turns into smaller and smaller particles, which eventually congeal into forming this kind of binary type object here. And what happens to all the little tiny planetesimals that scatter out of the system during formation is really what we're talking about here in terms of understanding the size distribution. We want to know basically how big are those binary components, and then how big is all the little material that flew out. So we're going to get that from the size distribution. This process of planetesimal formation seems to have happened ubiquitously, throughout the entire solar system from the asteroid belt outward. So probing how that works is a critical part of this. So NASA had a mission called New Horizons. It's still flying through the Kuiper Belt. We had this close approach to the Kuiper Belt object Arrokoth. And one of the things that you can see are all these little dots on Arrokoth, which are craters. There's the big crater up here called Sky, or sorry, no, the Sky crater's down here. There's Sky. But there's all these little tiny craters. When we count them up, we can get the impactor distribution. And from that, we can measure the very smallest objects in the outer solar system and the distribution of their sizes. And that tells us about planetesimal formation. And from the ground, we can get this component of the distribution. We can see how the size distribution is behaving at large n. So that's this kind of pink area with observations from CFHT. Then we can go all the way to the largest objects way over here, or sorry, the smallest objects, which are being probed by those kinds of observations from Arrokoth. And when we do that, what we start to see is that there's different models of that planetesimal formation process that can lead to different kind of behaviors in the middle. And so this middle zone, we have lots of different things going on. And that's what we want to probe with CASTOR. We want to measure that size distribution in that middle zone. The other thing we're going to be looking at is things like cometary activity. So here's a beautiful image of 67P that was taken by the Rosetta mission. And we have here the sort of the approach image, and then a closer up one here. And one thing I want to draw your attention to is look at how that's actually kind of like a binary system that's going on there. This is two objects that are basically have come together very much like that Arrokoth. But now this is factors of 10 smaller. So that's where this kind of process is happening at all different scales. By measuring cometary activity, what you're getting to is the kind of what's going on right here at the surface. How is the gas escaping? What are those bottom surface layers like? And of course, that tells us about what formed, what was able to, when the formation process was happening, what ices were able to be preserved on that surface. And that tells us about that primary sort of environment where the objects formed. This is Comet 67 Berdelli. Bernstein. This is an image that was taken with HST Weifel Camera 3. By taking these images and by getting actually spectra in the UV, we can really pick out the driving molecules of this cometary activity. So what we're going to do with CASTOR is we're going to take images, spectra of the cometary activity. We're going to measure this emission, and that emission is going to tell us about the driving materials of the cometary activity and tell us about what ices survive that thermal environment. So the survey we want to do with CASTOR, we want to look at the places in the solar system that are below declination 0 and that line up with the LSST. So Euclid is a mission that will be observing areas like this and up here that are off the ecliptic. Euclid's not going to look in the ecliptic. And then CASTOR will do a probe of this zone right here behind me and way over here, this area that's right near the ecliptic plane. And that probing of that ecliptic plane, that's going to give us measurements of thousands and thousands of Kuiper belt objects, an enormously high fidelity size distribution, and allow for measurement of their surface properties. And then when comets are found, we're going to do serendipitous observations where we're just going to slew over target opportunity and observe those cometary objects. And tying all that together is going to give us this chemistry and this physical environment from the formation of the solar system and really make an enormous impact in planetesimal formation. So thanks for those few minutes, and I hope the rest of the meeting goes well for you. And let's go CASTOR. Cheers.